So, hello everyone. My name is Albrecht. I'm a lead engineer and system responsible at Webasto Roof and Components. System responsible for the innovations and advanced engineering, so early development stage of electric heaters. And after a brief introduction of the company, I would like to show you our approach, how to improve thermal management systems in the future, how to develop them, and I will show you our approach, where we're standing, what we see as the benefit of this kind of component with an approach of integration, and how this can affect thermal management systems. So, first of all, the company Webasto, we are mostly active in the automotive industry, so it's our core business, with different business units, and the products, the majority of the biggest business we have is in the roof business. So we supply roofs to the automotive industry in different kinds of roofs, like for cabrios, so for convertibles, for example. We have huge market share, and in general panoramic roofs, for example, or also technological advances like the sensor integration for autonomic driving in our development. But we also have, which is probably the more known one to customers, is the thermal business. So in thermal business, we have been in the thermal business for decades, particularly in the fuel-operated heaters, which we're mostly known for, but also we are in the development and in the market with electric heating, so with the HVH since 2015. Also for 800 volts in 2019, we were the first ones to have an 800 volt heater on the market. And maybe not as much known, but also in the aftermarket, so special OEs, we also have systems, which are also our heaters, which we contribute there. But also we develop systems for smaller numbers, for example, for caravans, for marine, for trains. Also, we are in the truck business, where we also apply the components we develop in fuel and electric heating. But also we have fully developed, for example, HVACs or heat pumps, which we have there. And we take our knowledge from for our new developments. And last but not least, we also have a battery business. So we do not have our own battery cells, but we do the battery modules and full battery packs, which we deliver to OEM customers. So about the numbers, I already shared some of the information. Webasto is existing since 1901. Since 1935, we are in the heating business, and we have in total about 15,000 employees. Particularly in the heating business, we have more than 1,000 people working. So far, we have produced 25 million heating units and sold, and we also have plants and offices in different countries. Particularly for heating, we are in Germany. We have the headquarters with the development and also production and sales, but also, for example, in South Korea, Japan, China, and in the USA. Now, our idea when we take a look at the market, at the technical developments, we see some challenges we have to overcome. Right now, since the electromobility has grown a lot within the last decade, the requirements and kind of implementations has changed a lot. And particularly, we are now facing challenges through changes of coolants. For example, from the classic coolants, we now go to sometimes, for example, dielectric coolants, which have to be non-conductive. Also refrigerants also have been a lot of discussions today with the new, with propane, for example, coming up within the next years, maybe decades. Then also battery technologies. Battery technologies make a huge difference in the thermal management, because when we talk about thermal management, on one side we have the cabin, which needs thermal management, but on the other hand, the battery also needs conditioning, heating in particular, to operate at reasonable temperatures, and therefore ensure lifetime. And fast charging, on the other hand, needs some cooling capability. So when we talk about fast charging, for example, something around 400 kilowatt, then we always have some electrical losses that need to be cooled down. So when we have 400 kilowatt of charging capability, this means we have somewhere around 5 to 10% of electrical heat losses that need to be cooled down. This means 20 to 40 kilowatt are just heat generated by this fast charging process. And this heat needs to go somewhere. And the batteries have a range of temperature in which they need to operate. And while we need to condition it to work in a reasonable temperature range, this heating or this heat loss causes the temperature to rise further, and we need to cool it down. This is where a chiller comes into the application of electric vehicles, because if the ambient temperature is low, then we have a good temperature gradient to the ambient, and we can remove the heat from the system towards the ambient. But if, for example, we are driving in summer and, for example, drive to a holiday on a long way and need to charge on the highway because it's multiple hundred kilometers, then we do not want to wait for some hours for the battery to charge, but it should go fast within 10, 20 minutes. And but on the outside, when it's summer holidays, for example, it may be 30, 35, maybe even on the asphalt with the sun, it may be a higher temperature. And we always need to have a temperature gradient from the coolant of the battery towards the ambient to get a heat flux towards the ambient. And the temperature difference is small compared to other ambient temperatures. And this is where a heat pump often comes in place with a chiller, because with a chiller we can transport this heat towards the heat pump. And with a heat pump we have this temperature level of maybe around 40 degrees with the coolant temperature of the battery, which we can rise to 80, 90, 100 degree temperature on the high pressure side by using a compressor, by using a heat pump, and thus generating a temperature gap between the coolant or refrigerant and the ambient to get this temperature, to get this heat out of the vehicle. So chillers are a key component to achieving fast charging capabilities. And since we also need, on the other hand, heating capabilities in the systems to heat up the cabin, to heat up the battery, to get them on the proper temperature levels, this requires multiple components in the vehicles. And the vehicles, electric vehicles, have grown in their thermal management architecture for the last years. And right now, the challenge is we want to again reduce the thermal management systems to less components, to less weight again. So integrated approaches are one of the key challenges we want to achieve in the next years. And the heat pump, on the other side, is also, in our opinion, one of the key components for electric vehicles in general, because, as we already also heard today, range and energy consumption for heating is significant for electric vehicles. And with a heat pump, we have COPs bigger than 1, which means we do not need to spend as much electric power as we can achieve as heating power. We are using ambient temperature, ambient heat. And therefore, from our perspective, a thermal management system, including a heat pump, but also still requiring electric heating for conditioning the battery in particular, maybe also for the cabin at lower temperatures, is the key, or is the future. And other challenges that we always face is, for example, cost pressure. So reducing the costs is always important. Decarbonization, so getting carbon footprint as low as possible, achieving high COPs, for example, to reduce the energy needed for the thermal management. And in general, since we have been facing increasing speed or increasing speed of changes in the vehicles and the architectures, also innovation speed is key. So when we look at the thermal management system, as I mentioned, with the heat pump as a key component, a heat pump has a temperature-dependent amount of energy it can contribute to the system. It is dependent on the refrigerant. When you're talking about R1234YF today, then we have a temperature profile close to this. This is just an example. It always depends on the system, of course. But in general, the higher the temperature, the higher the ambient temperature, the higher also the heat available from the ambient is, and the more energy you can get into the vehicle, into the cabin. And for lower temperatures, the performance of the heat pump in general decreases. And as we can see then on the so the blue line is the energy available from the heat pump, and then here on the black line we can see how much energy is actually needed within the cabin in this example. So at high temperatures, the heat pump alone is sufficient to heat up the cabin and to keep it on temperature, but at low ambient temperatures there is a gap between the energy, the heat needed, and the heat supplied by the heat pump. So at low temperatures in particular, there's always a gap that needs to be covered by electric heating, which is also done nowadays by high voltage or by general air heaters or by water heaters. And even with new refrigerants, different refrigerants, CO2, propane, we have a shift in this curve. So in particular, we see with CO2 and propane that the blue curve will move to the left, will maybe also move up. There will still be a gap for particularly very low temperatures. And therefore, we also see different systems today on the market, depending on the OEM, depending on also the platforms. You see many different approaches how the thermal management system is done. One target is to heat the cabin. Today, it's often air heaters are used, also coolant heaters are used, and the heat pump is also in some vehicles in general seen. And we see that there will be more heat pumps also in the future. While for conditioning the battery, since there is no air flux or there's no air used in the battery, we usually see coolant heaters, and this heat is what we always have, or almost always have, coolant within the battery for the conditioning, and therefore see it always connected to either a water heater, coolant heater, or sometimes also different approaches, for example, using waste heat from other components. Then, when we use the heat pump, also there are different heat pump systems. You can have the heat pump either be connected directly to air as the source, so you can take up ambient energy directly from air, or maybe you have a coolant loop between your ambient heat exchanger and the refrigerant heat exchanger, and same goes for the cabin. For the cabin, this is particularly important when we talk about propane, because from regulations, we see that indirect systems with a coolant loop in between is necessary for propane to separate propane component or propane containing components and the cabin. And refrigerants, the three different ones I already talked about. So basically, you can see just as a combination of those options, you have 72 different systems, not even considering power levels yet, or particular structures within a vehicle. So how can we, what can we change in this kind of architecture, and what impact do we see? With our integration, functional integration approach, we combine a chiller. So we call it a heated chiller because it's basically one chiller as you can see here, it's a chiller stack at the top with a traditional heating function as a coolant heater. So in one component, we have the two functions of a chiller and coolant heating. But also, since we already implement heating, we can also provide the function of refrigerant heating. Refrigerant heating means that we can also supply the heat pump, and even if when we do not have energy or enough energy from the ambient to support the heat pump to keep the heat pump running, or if the performance is low, by heating the refrigerant, we can achieve this, keep the heat pump running, even at temperatures up to minus 40 degrees. So in classic automotive requirements. And therefore, when we have a look at the architecture, on the left side, we see a classic system. This could have a coolant heater. On the battery side, this could have an air heater for the cabin. So we have here a coolant heater for the battery. We have an air heater for the cabin, and we have a heat pump system. Basically, our heated chiller can replace all of those components and reduce it to one component. Of course, this is just one example architecture. Basically, whenever I show the slide, there's always a question, yeah, but my system does not look like this. For example, I do not have an air heater, or my architecture looks different. Of course, since for every customer we see a different architecture, this is almost never the one true answer. But also with the view on propane, or the high likeliness for propane in the future, we see this indirect system as one of the key ones. And when we compare our component to, let's say, only a coolant heater, it's a relatively simple comparison. So we want to compare also to, let's say, a more performance system, including a coolant and an air heater. So I also brought a video. Maybe can you please start it? To also show how the architecture changes and how the different use cases work. Okay, maybe I'll just skip it then. Now it's running. So you can see it also on the big scale. We combine chiller with coolant heating, particularly for battery heating as a coolant heater, and refrigerant heating. Therefore can merge what's basically at least two, maybe three components to one. And we can heat coolant for the battery right away with this component. We can heat the refrigerant to just have the heat pump running as a standalone in this case. And we can also, so this is for heating the cabin. And lastly, also battery cooling. When we have high temperatures of the coolant for the battery, we can use it in combination with the heat pump to get heat out of the system, get it to higher temperature levels using the heat pump, and therefore also maintain the classic chiller function. So the benefits we see, particularly on the system level, is you can reduce the amount of your components in the system. You can change your architectures, even simplify your architecture overall. Less components also means always less installation space, less weight, also lower costs, depending, of course, which kind of system you are coming from. If you, for example, save an air and a water heater, the impact is much more than by comparing it to just saving one water heater. And we also have some technical advantages, like since we have the classic coolant heating function, which compares one by one to a coolant heater. And with the refrigerant heating function, we can, for example, also have we can have a very fast reaction time by the heat pump to be able to start the heat pump right away with very small delay. and to run the compressor within just a few seconds by giving the heat to the system. The performance of the heated chiller is it has a cooling performance for the battery of 15 kilowatt, and it has some electric heating, so electric heat availability is 9 kilowatt, which we can distribute between coolant and refrigerant. And the capability of the single mediums is around 6 to 7 kilowatt for the coolant, and it's 5 to 6 kilowatt for the refrigerant. So in total, it's maximum of 9 kilowatt that can be heated into both medias in total, but it can be distributed and controlled by the media flow. So high volume flows mean always a high heat transfer, and therefore you can regulate how much heat goes into one medium, like into the refrigerant or the coolant. Other than that, for refrigerants, we are aiming particularly for R1234YF and propane. CO2 is, due to its higher pressure levels, this component would look a lot different. Basically, it's possible, but it's not within the size and shape we see here. And it fulfills general automotive requirements, so safety function with ASLB. And we have 800, or technology is usable for 800 volt, also for 400 volt, and usual lifetime safety requirements. Now, we have this component developed. We have a prototype, which you can also see here. We have approved that this concept is working. We also have approved that the performance is also the performance is also reached. And I want to show you some of the benefits in general. And so, as mentioned before, we compare the heated chiller to a reference system. In this case, we have test cases. Here we have also some simulation cases. And in a reference system, we compare to a system with a 6 kilowatt air heater and a 6 kilowatt coolant heater. And in our Webasto model, we have this heated chiller instead of the other two heaters with 9 kilowatt. And the heat pump, of course, in both systems. So what do we see in comparison? Let's start with the solid line. We see the temperatures here, and the yellow one is the line for the Webasto model. We see that the temperature of the cabin increasing much faster, so we overall have more heat available within the cabin. This simulation case is also prioritizing the cabin. So for example, if you aim for maximum comfort for the customer, for the driver, we aim for heating up the cabin as fast as possible. And therefore, we prioritize the cabin. We transport all the heat available to the refrigerant. And since as I mentioned, 5 to 6 kilowatt are transported to the refrigerant, we also have the compressor contributing. So at very low temperatures, for the air heater, the compressor is not going to contribute because the heat pump is not working at very low ambient temperatures. But here we can still utilize the compressor at any temperature. And therefore, the heat pump performance can be reaching up to around 9 kilowatt. 9 kilowatt, of course, is more than 6 kilowatts available by the air heater. And therefore, the cabin can be heated much faster. For the coolant, if you transport 6 kilowatt to the refrigerant, only 3 kilowatt is available to the coolant. Therefore, of course, the heating performance of the coolant is lower in this case. But as mentioned, we can also we can choose how much heat goes into which direction. So we can basically also increase the heat flux to the coolant up to 6 kilowatt and have then 3 kilowatt to the refrigerant. And including a compressor, we basically have the same numbers then for both systems. This is also why direct comparison with the coolant heater does not need to be done, because Basically, if I provide 6 kilowatt with the one system, 6 kilowatt with the other system, I do not have to distinguish between the two of them. Having a closer look at the power and the energy needed, then you can see this again in the yellow curve and the solid one, that okay, at the very beginning we need some time for the heat pump to reach the same performance level, because particularly on the high temperature side, on the high pressure side, there is some delay with the compressor, but we reach the performance level, the high performance level, quite fast. And then most of the time we have overall more heat available for the vehicle than in the reference system. The energy needed is at the same time higher, but this comes from the higher performance. So of course, higher performance takes more energy in the same time. And since we reach, for example, target temperature levels for the cabin at much faster times, you can, for example, go into a stationary level in which you, for example, only need the heat pump anymore without support heating, or need in general lower power over time. This balances out. And those are the benefits we see. Also, since we can keep the compressor, the heat pump, running at any ambient temperature, and also can contribute to the compressor at any temperature, we see advantages over the classic system with coolant heaters, with air heaters, but also compared to, for example, waste heat cases in which the compressor, for example, is used to also support with heat to the heat pump, even if it would not work under normal cases. But with a shortcut circuit, for example, we have the advantage that we can always support the compressor with heat, so with evaporated refrigerant, and make sure that there's never any liquid refrigerant coming to the compressor, making sure that the lifetime issues can be reduced, making sure that the noise level can be reduced, since we can also control the inlet condition for the compressor to always make sure that we have proper temperatures, proper evaporation, and proper pressure levels. And heat pump performance in general can be boosted. The compressor can always be used as one of the key components, as one of the contributors in the thermal management system. And on the system level, we can reduce complexity, volume, and cost. So thank you very much. And if you have any questions, you can ask or also talk to me later on. Also, I brought some colleague, Michel Wagner, if you want to get in contact. Thank you very much.